Hello all, this is VLSA updates. Hope you all are doing well. Okay, right now I'm in North India, so it's very cold out there. You must have to come and visit and enjoy the place. This is VLSA updates, and we have covered few sessions regarding the VLSA overview. And yesterday we saw some Vivardo, tool installation, how to get started with synthesize for FPGA, and how it will be useful for the freshers, and how they can get started with FPGA synthesize and to understand the entire flow and all. We saw a few more information on that. So today let's see what are the next steps to take in care, and how do we go forward for that. Okay, so let's just get started with that. Before that, let me share my screen. Okay, so this is what last time we saw, and different domains available in the VLSI: design, verification, and the physical design, and analog layout, and what are the skill sets are required, what are the variations are there, and what are the skill sets required for the engineers. And also we saw the acceleration platform for the emulation, and how it is important as the chip size are growing up, and how it is important to work on emulation platform, especially like FPGA based emulation, and the importance of FPGA understanding and the knowledge of having worked on FPGA platforms, and how it will be helping to ramp up the acceleration process in emulation platform, and how it is accelerating for the tap in, and how it is helping the environment to verify the complicated designs, and in a shorter amount of time compared to the traditional simulation environment. So having said that, FPGA plays a key role in emulation environment. So at the beginning it is very important to understand the hardware flow. So FPGA is a good place to start for you, and the way to practice and do synthesize on the FPGA platform, how the RTL is getting converted into the FPGA resources, and how it is getting mapped, how the complex designs are facing congestions and all. So anyway, the topic is not about FPGA completely here. I just wanted to emphasize little bit about that at the beginning level. Okay, so yeah, let's go over it. And also we are going to cover few basic skills required. I list down a few basic skills which is really important, and which are good to know the skills. Okay, so basics of digital logic design and the CMOS VLSI design, and hardware description language, having practiced any of the hardware description language, Verilog or VHDL, and hardware verification language, system Verilog, which is primarily used for the verification purpose, and any of the verification methodology, UVM or the OVM or something, and the programming language, which is high level programming language, C and C++. Okay, and scripting programming, Python, TCL or the Perl, and FPGA and ASIC design flow from the microarchitecture to the implementation point of view. Okay, and static timing analysis and clock domain crossing. Okay, these are the major skills we are covering, and good to know skills for any VLSI engineers before they move into design or verification or physical design or the layout. So these are the basic skills, good to know, and I just wanted to highlight those skills once again. Okay, so let's move to the next slide. So I wanted to cover it, what is the FPGA market going forward, and where and all it can be used. Okay, so it's mainly in the FPGA based applications are wide now, in the signal processing application, acceleration environment, and variety of areas nowadays choosing the FPGA platform due to its easy availability, and cost wise it's little high, but it's easily available, and you cannot directly go for any ASIC chip or any small applications. So those places FPGA can easily fill the gap and be useful for the engineers. Okay, and the bigger application is like the prototyping. um, Anyone nowadays can design their own chip. Okay, they can easily use the FPGA platform to validate the design before they go for the actual silicon. Okay, which gives the complete confidence that your design is working in the hardware platform as expected in the simulation that you expected before we actually go into the hardware. It will give you the complete clarity on that. So mainly used for the ASIC prototyping, and for the emulation purpose it is in the bigger in use nowadays, to validate the bigger SOCs by combining multiple FPGAs, and we can do that emulation platform also. Okay. So having said that, FPGA has the wide market as we move forward. So having good understanding on any of the major vendors like Xilinx and Intel, so will increase your opportunities, and you can use their platforms in any applications, and it will create wide opportunities for everyone. Okay. Yeah. So I wanted to cover one major topic which is called clock domain crossing. You all might be aware what's clock domain crossing and all. I just wanted to go over it, and there are two types of clock domain crossing. One is we can pass the single bit data, or we can pass the multi-bit data. Okay, and also we have another constraint, like whether we want to pass from slower domain to faster domain, or the faster domain to slower domain, and how it can be done. Okay, so we already have discussed a few major techniques can be used for the clock domain crossing and how it can be applied. Okay, so in this session I'm just going to cover a little bit overview on that and how it's going to be in the ground. Okay. Yeah, so for the clock domain crossing we have the source and destination, and let's say I'm having the clock frequency of 25 megahertz, and the other domain clock frequency is 60 megahertz, so which means like slower domain to the faster domain. And how it is going to pass the data, you can just imagine your clock frequency is slow. Here it's 25 megahertz, it's faster here. Okay, so for this kind of things we can use two flop synchronizer as shown here. It will work without any issues, and just an example, we have the slower clock and this is my faster clock. So I'm getting the data with respect to this slower clock domain, so there are high probability that I don't miss this data. I might get capture this data for two clock edges with respect to the faster domain, but there are no chances that I will miss this data. Okay, then why do we need two flops at the receiving end? You can ask the question, right? So for that there is a possibility, there's a high probability that we don't miss the data, but there is a possibility that your data might get captured, okay, at the clock edge, right? So if you see your data might get captured at the receiving end clock edge, so what happens during that time? It might create a violation, setup violation or the whole violation, right? So to avoid that, we have a two flop synchronizer, as we all are aware. Like in the first flop, your data might go into the metastable state. If suppose you are hitting into the violation here, this is my receiving clock domain. I'm just showing the example here, and in the first flop it will go into the metastable state, okay, and the second flop it will get captured in the second flop. Okay, so suppose there is a violation is hitting, and in the first flop your data might go into some unknown state, and then it will stable after some time with respect to the receiving clock domain. So eventually we will get to capture the actual data that we are expecting in the receiving clock domain. So for that we need to add additional flop here. In some cases we might have to go for 3 flop. If suppose the clock is faster, much faster, let's say the ratio is much faster. Here I'm just saying for 25 and 60 here. So if suppose your receiving domain clock frequency is much faster, 3 times or 4 times faster, like more than 100 megahertz clock here, so during that time, yeah, we need to go for 3 flop. There is a high probability that even the second stage also might go into metastable state, so we need to have to add one more flop. Okay, so to detect these kind of issues, there is a MTBF, mean time before failure formula. We can use that, and with the help of that we can detect how many flops we required basically. So normally we all go for 2 flop synchronizer, which are sufficient enough for our use cases. So I would recommend the 2 flop synchronizer. In the worst case we can think of 3 flop synchronizer here. Yeah, this is the slower to faster domain. So now let's ask the question, like, what will I do if I go for the faster to slower domain? There are 2 test cases for the faster to slower domain, just vice versa. If you see this clock diagram, this will be your sending domain. Your clocking is very fast here. Your data width could be only 1 clock cycle like this. Okay, so there is a high chance that your data might not get captured in the receiving domain. Okay, so how do we sort out this kind of problem? Okay, and you might send multiple data in the meantime without knowing whether the data is being received properly or not. To avoid that, we have the acknowledgement system, and from the source side we will request to the destination whether the destination is ready or not. Okay, and the destination will send an acknowledgement through again the 2 flop synchronizer by saying that the destination is ready to receive the data now, and the previous data is been received successfully through this acknowledgement. So after that we can send our new data. In that case we can make sure the previous data has been received successfully by the destination end, and it is ready to accept the new data. So the 2 things will get confirmed here. But here the challenge is, like, we will have to face a lot of latencies here. Like, we will have to send a request, and this will consume again 2 clock cycles, and we have to get back through that. It will take again 2 clock cycles here with respect to the source domain. Okay, there is a clock latencies are involved. For every transactions it might take 4 to 5 clock cycles to get back to us, and then we have to send the new data. It is the only disadvantage, but it will assure that your data is being received properly. Okay, so the other way is like we can go for the pulse stretching method. What it does, let's say your clock frequency is 75 MHz here, and the slower domain is 25 MHz. This is 3 times faster. Okay, so we have to stretch the input files to 3 clock cycle, minimum 3 clock cycles wider in the source domain, and send it to the destination domain. That's what we can do here. But here the one challenge is, like, we must sure that the clock frequencies are fixed, the ratios are fixed for 75 and 25. If suppose your requirement is changing, you wanted to increase the frequency during the runtime, at the same time you have to make sure this pulse stretching has been increased for one more clock cycle wider. So every time there will be a change, there is a change recorded in the RTL to make sure the pulse is being stretched for the number of clock cycles based on these frequency ratios. Okay, so that is the reason if the clock frequency ratios are fixed, and we can directly go for this pulse stretching method, and that's one thing. Okay, so but this is more efficient. Why? Because there won't be much latencies and all. We just have to expand the pulses in the sending domain. I will share you the code for this, and it's very simple logic for this. I can share you the logic in the answer forum. That will be very helpful for you guys. Okay. And the last thing I wanted to cover is the multi-bit data from the sending to receiving domain. Okay. In the multi-bit data, we can use asynchronous FIFO, which is more efficient, and inbuilt it will use a lot of great techniques, and write pointers or read pointers are one bit wider than the write address and the read address, and we need to use again the synchronizers, to detect the full and empty status across the clock domains. Okay, so all these things can be done, and but this is the efficient method to pass your multi-bit data from one clock domain to other clock domain. Yeah, so these are the major techniques we are using for the clock domain crossing. Let me put this way. Yeah. So write domain and the read domain, there will be two different clock frequencies, and for the fast write and the slow read, and we need to calculate the proper depth for the same, and this will provide us the proper transfer between the clock domains here. Okay, so yeah, I just wanted to show you the answers which I wrote already. That might be little helpful in the ground. We can always try for that. Yeah, just give me a minute, let me scroll down to the answer. We have the blog in Quora, so where we used to constantly update our answers, and also we post on LinkedIn also, so that people can see and get benefit from that. Okay, it's taking a lot of time. Maybe I can share this link in the LinkedIn or somewhere, so that you can see and get benefitful on that. Okay, yeah, just wanted to give a overcap on that and what we are having and what we are planning going forward, and how it's going to be helpful and all. Okay, so I think yeah, I can stop here, and then we can continue in the other topics, and please reach out in the meantime regarding FPGA or any design techniques, and any queries, any guidance, we'll be happy to help you all. Okay, thank you all, thanks for your time, it's nice connecting with you, and let's connect. Thank you, bye.